Mrs.W.Felcia Rajam, Assistant Professor, Department of Mathematics, Faculty of Science and Humanities, Bharat Institute of Higher Educational Research, is going to deliver the lecture on probability and stochastic process, topic probability theory. Deterministic experiment. There are experiments which always produce the same result, that is, unique outcome or unique events. Such experiments are known as deterministic. Random experiments. The experiments which do not produce the same result or outcome on every trial are called random experiments. Example, throwing an unbiased die, tossing a uniform unbiased coin. Outcome. In the study of probability, any process of observation is referred to as an experiment. The results of an observation are called the outcomes of an experiment. Trial and event. The performance of a random experiment is called a trial and the outcome is called an event. Example, throwing a coin is a trial and getting head or tail is an event. What is the meaning of a sample space? The totality of the possible outcomes of a random experiment is called the sample space of the experiment, and it will be denoted by capital S. Each outcomes or element of this sample space is known as the sample point or event. The number of sample points in a sample space is generally denoted by n of s. Example, tossing a coin. So the sample space S is equal to h comma t. So number of sample space is equal to 2. When we toss two coins simultaneously, then the sample space is equal to h comma h, h comma t, t comma h, t comma t. So the number of sample space is equals to 4. Rolling a die. We know that a die contains 6 sides. So the sample space S is equal to 1, 2, 3, 4, 5 and 6. So the number of sample space is equal to 6. Finite sample space. If the set of all possible outcomes of the experiment is finite, then the associated sample space is a finite sample space. Countably infinite. A sample space where the set of all outcomes can be put into a one-to-one correspondence with the natural numbers is said to be countably infinite. Countable or a discrete sample space. If a sample space is either finite or countably infinite, we say that it is a countable or a discrete sample space. Continuous. If the elements, or in other words we call it as points, of a sample space constitute a continuum, such as all the points on a line, then all the points on a line segment, all the points in a plane, then the sample space is said to be continuous. Equally likely events. The possibilities or events are said to be equally likely when we have no reason to expect any one rather than the other. Example, in tossing an unbiased coin, the head or the tail are equally likely. Mutually likely events or disjoint events. Two events A and B are said to be mutually exclusive events or disjoint events provided A intersection B is the null set. Note, if capital A and B are mutually exclusive, then it is not possible for both events to occur on the same trial. Example, in the throwing of a single dice, the events of getting 1, 2, 3, 4, 5, and 6 are mutually exclusive. Exhaustive events. Events are said to be exhaustive when they include all possibilities. Example, in tossing a coin, either the head or tail turns up. There is no other possibility, and therefore these are the exhaustive events. Favorable events. The trials which entail the happening of an event are said to be favorable to the events. Example, in the tossing of a die, the number of favorable events to the appearance of a multiple of 3 are 2, that is 3 and 6. Mathematical definition of probability. So probability is usually defined as P of A, which is also defined or denoted with capital P, which is equal to M by N, where M denotes the favorable number of cases and N denotes exhaustive number of cases. Permutation. Permutation means selection and arrangement of factors. The formula for the permutation is given by NPR is equal to n factorial divided by n minus r factorial. Permutations with repetitions. Let P of n, comma, n1, n2, etc. up to nr, which is equal to n factorial divided by n1 factorial, n2 factorial, etc. up to the last term nr factorial. An example, the number of permutations in the word radar is 5 factorial divided by 2 factorial into 2 factorial. The meaning is 5 denotes the number of letters in the word radar. So there are 5 number of words, 1, 2, 3, 4, 5, R-A-D-A-R, divided by 2 factorial. So 2 factorial denotes the number of R's in this word radar. So the first letter is R and the last letter is R. So altogether there are 2 numbers of R. So it denotes 2 factorial multiplied by 2 factorial. So the letter A is also repeated twice. So this denotes 2 factorial. When we take the factorial 5 factorial divided by 2 factorial into 2 factorial, the answer is equal to 30. Since there are 5 letters of which 2 are R and the 2 are A. Rule of sum. If an event can occur in m ways and another event can occur in n ways, there are m plus n ways in which exactly one event can occur. Example, consider a box containing 8 red balls and 5 green balls. Then we have 8 plus 5 ways. Choose either red ball or green ball. Rule of production. If there are m outcomes for event E and n possible outcomes for event E2, then there are mn outcomes for the composite event E1, E2. Combinations. Combinations means selection of factors. NCR into NPR divided by R factorial, which is equal to n factorial divided by n minus r factorial into r factorial. So the notation NCR is also denoted as C of n comma r or n r written column wise. Note, NCN is equal to NC0, which is equal to 1. NCR is equal to NCN minus R. NCX is equal to NCY, which implies N is equal to X plus Y or X is equal to Y. Statistical or empirical probability. If in n trials an event E happen m times, then the probability of the happening of E event is given by P. Probability is denoted by capital P, which is equal to P of E, which is equal to limit n tends to infinity m by n. Next one, axioms of probability. Axiom 1. Probability lies within 0 and 1. So it is given as 0 less than or equal to P of E less than or equal to 1. Axiom 2. Probability of yes is equal to 1. Axiom 3. For any sequence of mutually exclusive events E1, E2, that is, events for which EI, EJ is equal to a null set when I is not equal to J. EI, EJ is equal to 5 when I not equal to J. That is, probability of union I equal to 1 to infinity, EI is equal to summation I equal to 1 to infinity, EI. We refer to probability of E as the probability of the event, capital E. Theorem 1. The probability of an impossible event is 0 or the null event has probability 0. So the null event has the probability 0. So it is given by notation probability of the null event is equal to 0. Theorem 2. If A power C is the complementary event of A, probability of A power C is equal to 1 minus probability of A less than or equal to 1. Next theorem. If B is contained in A, probability of B is less than or equal to probability of A. Theorem 4. Addition law of probability. If A and B are any two events and are not disjoint, then probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Theorem 5. If A and B are any three events, then probability of A union B union C is equal to probability of A plus probability of B into probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of A intersection B intersection C. Theorem 6. If A1, A2, etc. AN are n mutually exclusive events, then the probability of the happening of one of them is probability of A1 union A2 union etc. AN. Probability of A1 plus probability of A2 plus etc. probability of AN. Multiplication theorem. If two events A and B are independent and can happen simultaneously, the probability of their joint occurrence, probability of A intersection B is equal to probability of A into probability of B. The theorem can be extended 3 or more events. This theorem can be extended to 3 or more events. Note, probability of A is equal to n of A divided by n of S. Mutually exclusive events or disjoint events is given by probability of A union B is equal to probability of A plus probability of B, or probability of A plus B equal to probability of A plus probability of B. Not mutually exclusive independent events. Probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. Probability of A intersection B is equal to probability of A into probability of B. Problem number 1. Find the probability of throwing first subdivision 4, second B an odd number, third C an even number with an ordinary die, that is 6-faced. That is, one die has 6 faces. Solution. When we draw or when we throw a die, there is only one way of getting 4 because a die has 6 faces. So there is only one face which turns up to 4. So the probability is given by number of favorable events divided by number of exhaustive events, which is equal to 1 by 6. Second subdivision, they have asked as an odd number. So the total number of ways of falling a die is equal to 6. Number of ways of falling is 1, 3, 5, which is equal to 3. So these are the odd numbers 1, 3, 5. So the total number of odd numbers is equal to 3. So probability is equal to number of favorable events divided by number of exhaustive events, which is equal to 3 by 6 equal to 1 by 2. Total number of ways of falling a die equal to 6. Number of ways of falling 2, 4, 6 that are even numbers. So then you get the answer to be 3. So the total probability is equal to 3 by 6, which is equal to 1 by 2. Problem number 2. Find the probability of a card drawn at random from an ordinary pack is a diamond. Solution. The total number of ways of getting one card is equal to 52. Number of ways of getting one diamond card is 13. Totally there are 13 diamond cards. So we get the number of ways of getting one diamond card is 13. So the probability is number of favorable events divided by number of exhaustive events, which is equal to 13 by 52 equal to 1 by 4. Problem. Next one. A bag contains 7 white, 6 red, and 5 black balls. 2 balls are drawn at random. Find the probability that they both will be white. Solution. The total number of balls is equal to 7 plus 6 plus 5, which is equal to 8. That is 7 white, 6 red, and 5 black balls. From these 18 balls, 2 balls can be drawn in 18C2 ways. So 18C2, if we calculate, you get the answer as 18 into 17 divided by 1.2, 1 into 2. The answer is equal to 153. Therefore, total number of ways of drawing 2 balls is equal to 153. 2 white balls can be drawn from 7 white balls in 7C2 ways. So 7C2 calculation, you get the answer to be 21 ways. Therefore, the number of favorable cases is equal to 21. Probability of drawing 2 white balls is equal to number of favorable cases divided by total number of cases, which is equal to number of favorable cases is 21 divided by total number of cases is 153. So which is equal to, after simplification, 7 by 51. Next problem. A person is known to hit the target in 3 out of 4 shots, whereas another person is known to hit the target in 2 out of 3 shots. Find the probability of the targets being hit at all when the both person try. Solution. The probability that the second person hit the target is equal to P of A is equal to 3 by 4. The probability that the second person hits the target, second person is denoted by P of B, which is equal to 2 by 3. The two events are not mutually exclusive since both person hits the same target. So the required probability P of A or B is equal to, according to the formula, P of A plus P of B minus P of A and B, which is equal to A, meaning is multiplication, which is equal to P of A value is 3 by 4 plus P of B value is 2 by 3 minus P of A is 3 by 4 into 2 by 3. So since A and B are independent, so if you do the calculation, 3 by 4 plus 2 by 3, the answer is 17 by 12. The LCM is 12 minus 3 by 4 into 2 by 3. 3 2s are 6 by 4 3s are 12. So if you take the LCM, you get it as 11 by 12. That is 17 minus 6 is 11 divided by the common LCM 12. Next problem. What is the chance that a leap year selected at random will contain 53 Sundays? A leap year consists of 366 days. Out of these 366 days, we have 52 full weeks. Hence, we have 52 Sundays definitely, because each week contains a Sunday. After that, you have 2 days extra. So those 2 days may be a combination of Monday, Tuesday, Tuesday, Wednesday, Wednesday, Thursday, Thursday, Friday, Friday, Saturday, Saturday, Sunday, and Sunday, Monday. Out of these 7 combinations, we can see the last 2 combinations contain Sunday. Hence, we have 2 favorable cases. So the probability is equal to 2 by 7. Next problem. An integer is chosen from 2 to 15. What is the probability that it is prime? Since there are 14 numbers from 2 to 15, the total number is 14. Out of 14 numbers, 2, 3, 5, 7, 11, 13 are prime numbers. So the number of prime numbers is equal to 6. Therefore, the probability that the number chosen is prime is equal to number of favorable numbers divided by total numbers. Next problem. 2 dice are thrown together. Find the probability that we get a total of 9. Here, the total number of outcomes is equal to 6 into 6, which is equal to 36. Total number 9 will come if we consider the outcomes as 3, 6, 4, 5, 5, 4, and 6, 3. That is, if you add these combinations, we will get a total of 9. For example, 3 plus 6 is 9, 4 plus 5 is 9, 5 plus 4 is 9, 6 plus 3 is also 9. These are the 4 cases. Hence, the required probability is equal to 4 by 36, which is equal to The answer 1 by 9. Next problem. Out of a sample of 200 items, 20 items are found to be defective. Find the probability that an item chosen at random from the sample is not defective. 20 items out of 200 items are defective. Out of the total 200, we have 20 items which are defective. So, the probability that an item chosen is defective is equal to 20 by 200. Hence, the probability that an item chosen is defective is equal to 1 minus 1 by 10. So 1 minus 1 by 10, if you take the LCM, 10 minus 1 by 10, 10 minus 1 is 9, 9 by 10. So these are the problems in which we have discussed how to take the probability for throwing 2 dice, then choosing an integer. The integer, it should be a prime number. Then in this problem, what is the chance that a leap year selected at random will contain 53 Sundays? So the main concept in this problem is a leap year. So leap year consists of 366 days. So from that we have chosen only 52 full weeks which contains 52 Sundays. And the previous problem, that is, we have 2 people who hit a target in 3 out of 4 shots. So then we get the solution as 11 by 12. So these problems help us to find the probability which will be useful for the entire topic. Thank you.